In the last lecture, we talked about the problem of thermodynamic reductionism. That is to say, the problem of whether or not thermodynamics can be derived as a consequence of statistical mechanics. And we talked about the fact that there are two main approaches to solving that problem, the Gibbsian approach and the Boltzmannian approach. In the Gibbsian approach, we focused on ensembles of systems, or at least on probability measures on phase spaces, whereas in the Boltzmannian approach, we focused on the concept of macrostates and the system exploring macrostates over time. Now, I did mention that physicists often prefer the Gibbs approach, and for that reason, that's the one that I'm going to follow here. I also, it is the approach to which I think I myself would subscribe, but more importantly, it's going to allow you to connect to other references in the physics literature. So let's remind ourselves of what the situation there in classical mechanics. So we have a classical phase space, which we'll call M, and we're going to assume that we're somehow able to equilibrate the system, which is to say, whatever probability density function it starts with, it will evolve to a uniform probability density function on the subset of phase space that we know that it can be in, which typically will be the subset with some specific energy. So let's suppose that we have either constant or near constant energy, and we can say that this annulus represents the part of phase space with near constant energy U. And so we're going to assume that we have a uniform PDF on this annulus in this case. Now, what we're claiming is that in thermodynamics, quantities can depend on things that we could derive from that probability measure. So, for instance, expectation values under this probability density function, moments of the probability density function would be fair game. But individual aspects of points of phase space, so like a function on phase space, would not immediately be actually detectable within thermodynamics. Good. Okay, now the next thing that we need to do, basically because this is going to be much more helpful as we actually try to work with systems in statistical mechanics, is think about this in quantum mechanics. I mentioned this a little bit in the last lecture, but here we're going to have to confront the problem. Now, I'm not going to go back and rederive everything for quantum mechanics. I'm just basically going to tell you how things work. What I'm going to assume is that we have a quantum space that either has a finite dimensional Hilbert space or has a set of has a Hamiltonian, sorry, with a discrete set of eigenstates. So for those of you who haven't taken quantum mechanics, we have a set of allowed energy levels. And what I'm saying is that that set cannot be continuous. Instead, it must at least be discrete. And it could be finite. Okay, so quantum version. So the Hilbert space H is finite dimensional or has discrete energy levels for our Hamiltonian. Wonderful. Now, what this gives us is that if we are looking at a given energy level, that energy level might have several states that achieve it. So, for instance, let's just draw something schematic. So the x-axis is actually going to mean nothing here, but the y-axis is going to denote the different energy levels. And these don't need to be evenly spaced. They can be spaced however. So maybe this level has one state in it. This level has three states in it. This level has 1 state in it. This level has 2. Maybe this one has 4. 1 and 1 again. Why not? Now the statement here would be that we have a uniform distribution over the allowed states, which typically will mean the states at the fixed energy that we know the system has. So for instance, if we know the system is at this state, maybe I should label these. So this 1, 2, 3, 4, 5. So if we know it's at energy level 5, then it has a uniform distribution of being in any of these 4 states. So a quarter chance of being in any of these 4 states. Now sometimes a set of states with a probability distribution on them in quantum mechanics is called a mixed state. But to avoid introducing unnecessary jargon, I'm not going to use that term here anymore. All I'll say is that we have some uniform distribution over those 4 states. Good. All right, so now we're ready to go on and think about deriving entropy, which we said was really most of our whole goal as we work in statistical mechanics to derive thermodynamic properties. Recall, that the entropy was defined to be, and this is the Gibbs entropy, which I'll denote here by SG, although I'll probably drop the G later, minus KB integral of F log F, where F is our continuous PDF on phase space, over our phase space M. But here in quantum mechanics, things are going to be a little bit different. So in QM, we'll instead have that SG is equal to, well, it'll be minus KB, and now this will turn into a sum since our probability distribution here now has become discrete. So it'll be the sum over allowed states, and this shouldn't have been M, it's whatever allowed region we have. Or you could have combined that into F, however we want to do it. But here I'll just say the sum over allowed states of P log P. So maybe allowed states S, probability of S log PS. Good. But I've just said that by our assumption that we've reached equilibrium, PS is simply going to be the number of 1 over the number of allowed states. So if we say the number of allowed states is by definition equal to N sub S, no, I guess we shouldn't have it be N sub S, just N, then SG is equal to minus KB, sum over allowed states S of 1 over N log 1 over N. But we can rearrange this a bit. Notice, first of all, that this doesn't depend on the state S at all. And so this sum just becomes the sum and times however many terms there are. But there are exactly n terms here. So we get an n here canceling this n here. Moreover, log of 1 over n is minus log of n. That minus sign cancels this minus sign. So in the end, we just get kb log of n. Now that's really cool because you'll notice that it matches the entropy that we defined for the Boltzmann approach in the last lecture. I'm not going to go into detail about why that is since we're not going to follow the Boltzmann approach anymore, but it does show that these two approaches really do give us very similar behavior. Okay, so now that we have this, our whole goal for working with individual systems is going to be to look at them to see how many energy eigenstates we get for a given energy level, and then to proceed from there just to find S. So I'm going to get the board erased, and then we'll work through our simplest example. Okay, In the past, we've talked about the Ising model. So in the Ising model, and here I've depicted it in one dimension, which is what we'll think about for now, you have a number of spins, and these spins can either be pointed up or down. Now, the spins pick up energy, typically, from being aligned in the same direction or being aligned opposite to each other. So it'll be positive energy if they're opposite aligned, negative energy if they're aligned with each other. They also might respond to an external magnetic field, which we can say is H pointing up without loss of generality. Okay, so in this case, I actually want to look at a specific special case of the Ising model, which is called the ideal paramagnet. And this case is what we get when we turn the energy that they get from aligning with each other to 0. So now, all that they want to do is align with the magnetic field. And you'll notice that whereas before it mattered that we were in 1D, so that they were only trying to align with their nearest neighbors, now it doesn't matter what dimension they're in. We only care about the total number that we have, which we'll say is n. And we also do still need to specify their magnetic moment mu. Wonderful. So, even if you know no quantum mechanics, this system is actually going to be really pretty easy to understand. We will use the sort of quantum style treatment, but all we need to think about is what the states are and then what the energy of each state is. Okay, so let's spell those things out. So a state is going to be a list. We could say it like this. We could say up, down, up, right? And then maybe this last one is up, where there are n total up-downs. Good. Another way to state the same information would be to give zeros or ones, right? So a set of, and maybe I should have said this is a representative state, not the set of states. I'll do the same thing here. Okay, so 0, 1, 1. Good. And then there are n bits. Excellent. And maybe one last way is we could have, instead of 0 and 1, done 1 and negative 1. And yeah, maybe I'll switch to that. So let me turn these zeros into negative 1s, and you'll see why I want to do that in a second. The answer is because I want to work out the energy that each state has. We'll notice that the energy that a single spin gets from being aligned with the magnetic field, so energy at site, let's say k, is, let me say S sub k, which is going to be 1 if we're up, and minus 1 if we're down, times h times mu, but then times minus 1. And that's because if the spin is aligned up, it should actually have negative potential energy from being correctly aligned with the magnetic field. Okay, so the energy now, if I think of this as being a sequence, an n-length sequence, S sub k, then the energy would be the sum over k from 1 to n of minus h mu sk. Good. Okay. So far so good. But there's a problem. Now we want to identify all of the, so if we fix the energy at a given value, so suppose we fix the desired energy to be u. Okay, now we want to see how many states there are with this energy. And to do that, we need to see how many states have this energy here, or using this formula here. Okay, so in other words, number of solutions to U is equal to minus H mu Sk sum K1 to N. Okay, to make our lives a little bit simpler, let's set U equal to, well, we know it'll have to be some integer multiple of H mu. So let's just set it to, maybe capital A, H mu, such that A is a, well, I guess it doesn't have to be a positive integer. It's just some integer. And if that's the case, let's come up here. Well, we can cancel H mu on both sides. So the same question is, number of solutions to minus A is equal to the sum O from K is equal to 1 to N of Sk. Now, it turns out to be very important from the quantum point of view that these particles are distinguishable from each other. In other words, if this is the K equals 3 site and this is the K equals 6 site, we can tell those two spins apart. We can just look at one or look at the other. This turns out not to be a feature of all systems in quantum mechanics. Now, a problem like this, where we're looking at an equation and trying to figure out its number of solutions, is some of the bread and butter of the field of combinatorics. And it turns out that that will come up all the time as we work in this setting. Okay, so how are we going to approach this? The answer is that we're helped out a lot by the fact that Sk cannot just be any numbers. They have to be plus or minus 1. So what I want to think about is that to achieve minus A means that we're going to, if we have n sort of chances, we're going to need to go to the right, if I want to think about it in that way, yes, to the right some number of times, and then to the left some number of times, such that right plus left is equal to minus A. So let me think about that for a second. N right minus n left is equal to minus A. And n right plus n left is equal to n. Good. Okay, so now let's think about that for a second. If I sum these together, I can kind of solve for n right or n left. So altogether, I get that n right is equal to, well, I would sum these together and then take half. So half n minus A. And n left, well, I need to take n minus A, so n plus A, and then have that. Great. So this is the number of times I need Sk to be positive 1, and this is the number of times I need Sk to be negative 1. Great. And this should work out. The problem is that it does matter where these positive and negative ones occur. So what we need to think about is all of the different ways of choosing exactly this many positive ones. Because once we've chosen those positive ones, then the negative ones come for free. So this is all getting a little bit abstract. So let's come up with a concrete example. So let's say that minus A is equal to, let's say it's 4. And we have n is equal to 7. Okay, so let's think about that. We want to get 4 to the right on net, And we know we need to take 7 total steps. And I'm just realizing my mistake here. I know that they should have the same parity, so I can't have n being 7. N is going to need to be 8. Good. Okay, well, that's not too bad. I know what I'm going to need to do is take 6 to the right and then 2 back. So let's think about one way I could do that. I could have S1 is equal to, so this is just an example, S1 is to the right, so is up. S2 is down, why not? S3 is up again. S4 is up again. Now I'm going to need another down, so let me maybe use this one here. S5 is going to be down. And finally, S6 will have to be up, such that I have 2 downs and the rest are all up. And that will give me minus A is equal to 4. Good. But this isn't the only way to do it. So really, now we've pushed the problem one step further to counting how many ways there are to do this. And fortunately, that is really just counting the number of ways to put these 6 right-moving ones. 1, 2, 3, 4, oops, and it's supposed to be 8. 5, 6, among 8 possibilities. The number of ways to choose an R from N is, some of you may have seen this before, it's the binomial coefficient n sub nr, or n choose nr. And the fact that it's called choose maybe should alert you to what's going on here. It's exactly the number of ways to make this choice. All right, I'm going to erase the board and finish this off. So on the last board, we finally proved this equality, that the number of solutions we get for this particular energy U is given by this choose function. So I've replaced U with a sort of non-dimensionalized version A, and then it turns out that in order to make this all work out, we just use this choose function with A inserted as one of the arguments. Okay, and this gives us the entropy. Wonderful. Well, it almost gives us the entropy. Recall that our formula tells us that S is equal to KB log this number. So if I call this little n, what I need to find is n. And actually, I'm going to replace that terminology of little n with one that's a bit more standard, which is omega. And since omega depends on U, let me subscript it with U as well. Okay, so let's find that. And this gives us S is equal to KB times the log of this thing. N, choose 1/2 n minus U over H mu. I'll just do that replacement right now. Great. Okay, and to some degree, we're done. We're done here. This is the exact answer to this question. But the problem is that if you remember this definition, it's pretty ugly. So this is n. This is the definition of n choose k. It's n factorial over k factorial times n minus k factorial. So that's a lot of logs of factorials. And those might look a little bit gross. I mean, certainly for big integers, we're not going to be able to compute n factorial exactly. There must be a better way. And in fact, there is. Although I'm not going to do the proof here, by using a particular approximation, we can make these logs of factorials much, much nicer. So we're going to use what's called Stirling's approximation. And we're going to use this all over the place in StatMech. So this is definitely something that's good to internalize if you can. And this is not a Taylor expansion. It's another type of approximation scheme called a saddle point approximation scheme. Again, I'm not going to go into a ton of detail here, but this basically works as long as n is sufficiently large. Okay, so what do we get? Log of n factorial. I'm going to use this tilde because I don't want to be sort of super careful about what this means, but I will say goes like n times the log of n minus n. Excellent. And we have a corollary here as well for the choose function. Notice that the log of the choose function, n choose k, is equal to the log of n factorial over k factorial times n minus k factorial, which then goes like by this statement. Well, it'll be, all we need to do is break this log up using log rules. So we'll have log of n factorial minus log of k factorial minus log of n minus k factorial. Okay, so then this will be like n log n minus n. Let me sort these into rows. Minus k log k plus k minus n minus k log n minus k plus n minus k. But check it out, we get a bunch of cancellations. This minus n cancels with this plus n, and this plus k cancels with this minus k, such that we just get that this is n log n minus k log k minus n minus k log n minus k. Excellent. Now, if we use this version, we can finally find a good approximation for the entropy of the ideal paramagnet when both n and a are relatively large. So that is our one condition here. So maybe I should put this up here. For n large. And then here, for n and k large. And to be a little bit more specific, n needs to be much larger than k, but k also needs to be large. Okay, anyway, so S is approximately equal to, for our case, KB times times n log n, okay, minus 1/2 n minus u over h mu log of the same thing, okay, and then minus n minus this. But notice that n minus this is going to, well, let's work it out in a little margin. So n minus 1/2 n plus 1, yes, no, that's right, plus u over h mu is equal to 1/2 n plus u over h mu. All right. So we get 1/2 n plus u over h mu log 1/2 n plus u over h mu. Excellent. And there we have it. One of the first entropies that we're going to be able to derive exactly, or at least exactly here and then approximately here using Stirling's approximation in statistical mechanics. And what I should say about this is that even though a lot of what we've done here has been a little bit sketchy in terms of getting to equilibrium, so doing all of these things in the Gibbs approach or the Boltzmann approach if we decide to take that, these entropies that we get here can now be tested using thermodynamics. We can create a system whose thermodynamics we can then measure in a lab by looking at things like heat capacities. And stunningly, even though we did a lot of sketchy math, these do end up sort of working out when tested in this way. And this is one of the big sort of surprises about thermodynamics. Anyway, in the next video, we'll get to another example. But until then, thank you so much for watching.